Hello and welcome. Today we're jumping into a super important topic, the structure of the atom. Now I know what you're thinking, but trust me, this is a topic that shows up everywhere in your WAEC, NECO, and JAMB Physics exams. Getting this right is absolutely key to smashing that paper. So are you ready? Let's get right into it. So you might be asking, Sir, why are we spending so much time on this one topic? That's a great question. Well, it's because the ideas from atomic structure are like the foundation of a house. So many other topics, we're talking electricity, light, even nuclear physics, they all connect right back here. So if you master this, it's like you're collecting guaranteed marks before you even walk into the exam hall. You can definitely do this. All right, here's our game plan for today. First, we'll look at the exam blueprint, what the syllabus actually says. Then, we'll dive into the story of the atom. After that, we'll tackle some key concepts about energy and electrons. Then, the best part, we'll solve real exam questions together. And finally, we'll wrap up with a quick summary and my top tips. Let's go. Now, just so we're all on the same page, we are not just teaching random things here. Everything we're covering today is taken straight from your official WAEC, NECO, and JAMB syllabus. You see these points? Atomic models, energy levels, the photoelectric effects. This is exactly what the examiners expect you to know. This is your roadmap to success. No guesswork involved. Okay, let's get into the main lesson. We're going to start with a story, the story of the atom. Now, this isn't just a history lesson, okay? Understanding how our idea of the atom changed over time is crucial because the examiners love to ask theory questions about the different models and, more importantly, their weaknesses. So, this story has a few main characters. It all kicked off with Thomson back in 1904. Then Rutherford came along in 1911 and completely changed the game. After him, Bohr stepped in around 1913 to fix some major problems. And that leads us all the way to the modern quantum model from Schrödinger. Let's break each of these down. First up, we have J.J. Thomson's model. He called it the plum pudding model. You can think of it like a fruit cake. You know, the whole cake is a ball of positive charge, and the fruits inside are the negatively charged electrons scattered around. It was a decent first guess because it explained why atoms are neutral, but it had a big problem. It completely failed to explain what happened in Rutherford's next big experiment. And that brings us to Ernest Rutherford. This guy did something amazing. He took tiny alpha particles and shot them at a super thin sheet of gold foil. He expected them all to pass straight through, like bullets through paper. But some of them bounced right back. It was shocking. This discovery meant that all the positive charge in an atom must be packed into a tiny, dense spot in the middle, which he called the nucleus. But his model had a huge flaw. If electrons were orbiting this nucleus, why didn't they lose energy and spiral to their doom? His model couldn't explain why atoms are stable at all. So, to solve this puzzle, in comes Niels Bohr. He suggested something totally revolutionary. He said, hold on, maybe electrons can't just be anywhere. He proposed that they exist only in specific fixed energy levels, kind of like planets and orbits. An electron can stay in one of these special orbits forever without losing energy. It only absorbs or gives off energy when it makes a quantum leap from one level to another. This single idea was the beginning of a whole new way of thinking about physics. And here's the best part for us exam candidates. For the simple hydrogen atom, Bohr didn't just have an idea. He gave us a formula to calculate the energy of each of those levels. The energy of any level n is just minus 13.6 divided by n squared. That n is just the level number, 1, 2, 3, and so on. The unit is electron volts, or eV. This formula right here, it's pure gold for calculation questions. You need to know it. So let's put that formula to work with an example. An electron drops from the second level, so n equals 2, down to the first level, n equals 1. What's the energy of the light it spits out? Well, first we find the energy of level 2. That's minus 13.6 divided by 2 squared, which gives us minus 3.4 eV. Then we find the energy of level 1. That's minus 13.6 divided by 1 squared, which is just minus 13.6 eV. The energy of the photon is the difference between where it started and where it ended. So, minus 3.4 minus 13.6. And remember, a minus is a plus. That gives us a final answer of 10.2 eV. See? Simple. Excellent work. You're getting the hang of this. Now that we've gone through the history of the models, let's look at a few other key ideas about energy, electrons, and light. Pay close attention here because these are concepts the examiners absolutely love to ask about. Okay, this next one might bend your brain a little bit, but it's so important. It's called wave-particle duality. It basically says that tiny things, like electrons, which we normally think of as little balls or particles, can sometimes act like waves. And at the same time, light, which we think of as a wave, can sometimes act like a particle, which we call a photon. It's weird, I know, but it's how the universe works. And let me tell you, JAMB especially loves to ask conceptual questions about this idea. Alright, let's talk about how to get electrons to leave a piece of metal. There are two main ways you need to know. The first is thermoionic emission. The clue is in the name. Therm means heat. You just heat the metal up until the electrons get so much energy they jump right out. Remember those old big back TVs? That's thermoionic emission at work. The second way is the photoelectric effect. Here, photo means light. You shine a light with enough energy onto the metal and bam, it knocks an electron out. This is the amazing principle that makes solar panels work. And speaking of the photoelectric effect, you cannot talk about it without this powerful equation from the great Albert Einstein. It looks simple, but it's genius. It says HF equals phi O plus KE max. Let's break it down. Think of it like a budget. HF is the total energy the light particle gives to the electron. The metal takes a fee, or a tax, to release the electron. That's the work function. Phi O. Whatever energy is left over, that's the electron's moving energy. Its maximum kinetic energy. This equation is a guaranteed calculation question, so know it inside and out. Let's quickly touch on X-rays. For your exams, you absolutely have to know two things: how they are made and what their properties are. To mark them, you get electrons moving really fast and then you slam them into a metal target. It's like a high-speed car crash for electrons. And for their properties, just remember these three. They are high-energy waves, they have no charge, so they don't bend in electric or magnetic fields, and they can go through your skin, but not your bones. That's why they are so useful in hospitals. Alright, theory is one thing, but applying it is where the real marks are. This is the moment you've all been waiting for. We're about to tackle real past questions from WAEC, NECO, and JAMB. This is where the rubber meets the road, and you will see exactly how these ideas show up in your exam. Let's start with this one. This is a real theory question from WAEC 2022. It's asking for the force between the electron and proton in a hydrogen atom. Now look closely. What do you see? They've mixed atomic structure with another topic, electrostatics. This is a classic examiner's trick to see if you can connect ideas from different parts of the syllabus. So, how do we attack this? The first thing that should pop into your head is the formula that connects force, charge, and distance. That's right, it's Coulomb's law. F equals kq1 q2 all over r squared. Then it's just a matter of plugging in the numbers. But wait, I want to warn you about a very common mistake. So many students forget to square the distance r. Please, don't let that be you. Double check your work. When you do it correctly, you get the final answer of 8.52 times 10 to the power of minus 8 newtons. Okay, next up, a NECO question. This one isn't a calculation. It's a pure test of your understanding of Bohr's theory. It gives you 3 statements and asks which of them are correct. Let's go through each one by one and see if they hold up. Let's analyze this. Statement 1. The electron moves without radiating energy. Is that true for Bohr's model? Yes, that's the whole idea of stable orbit, so statement 1 is correct. Statement 2. Angular momentum is quantized. Yes, that's another one of Bohr's key postulates. Correct again. And statement 3. Energy cannot vary continuously. Absolutely true. That's the core idea of discrete energy levels. So since I, and 3 are all correct, our answer has to be E. See? Knowing your theory pays off directly in marks.
And now for a JAMB question. You know, JAMB, they sometimes like to bring in a little bit of chemistry just to test you. This one asks about something called the azimuthal quantum number for a chromium atom. Now, don't panic when you see words like that. It sounds complicated, but it's really just a fancy way of asking about electron configuration, something you've probably covered in chemistry class. So here's how we solve it. First, we have to write out the electron configuration for chromium. Now, remember, chromium is one of those special exceptions. Its configuration ends in 4s1, 3d5 for extra stability. You just have to memorize that one. Next, you need to know what the L numbers mean. Just remember this. L equals 1 means p orbitals, and L equals 2 means d orbitals. Now we just count. How many electrons are in p orbitals? We have 6 in 2p and 6 in 3p. That's a total of 12. And how many in d orbitals? Just 5 in 3D. So the answer is 12 and 5. Whew, we have covered so much ground today, and you've all done an amazing job keeping up. Now, to make sure all this information sticks, let's bring it all together in a final summary. I'm also going to give you my top tips to carry with you into the exam hall. This is how we lock in the knowledge for good. This slide right here is your ultimate revision cheat sheet. You might even want to take a screenshot. For atomic models, you must be able to draw them and state their limitations. WAEC loves that. For the photoelectric effect, that's formula HF equals phi O plus KE max must be in your head. And please, don't mix up work function with threshold frequency. One is energy, the other is frequency. And finally, wave-particle duality. Just know that JAMB loves this concept for their tricky theory questions. Keep these tips close. If you found this lesson helpful, please do me a huge favor. Like this video, share it with your classmates and friends who are also preparing for WAEC, NECO, and JAMB, and subscribe to our YouTube channel right now so you don't miss out on the next topic. Also, don't forget to visit www.examkp.com for thousands of free practice questions and answers. You've got this. Let's go and smash these exams together.